Balancing redox reactions in organic chemistry is actually fairly difficult. Case in point, here is a typical benzylic oxidation where we take toluene and we convert that into the carboxylic acid into benzoic acid using potassium permanganate in acidic media. But the question is, what is the actual ratio of our reagents here? Is it 1:1, 1:2, 2:1? While we hardly ever balance our reactions on paper, it is an essential step if you want to set this reaction in the lab. So let's look at how to properly balance these reactions. Here I'm going to be using the half reaction method, and the first thing that I'm going to write out is the oxidation process. So for my oxidation, we are taking the toluene and we are converting that into the carboxylic acid. In order to balance this portion of our reaction, we are going to be using water and H+ ions. And as a general rule of thumb, if we are working in acidic conditions, it is always going to be H+ and water. If we were to do the reaction in basic conditions, that would be OH- and water. So since we use acid here, we'll use water and H+. So in order to properly use my water and H+, I see that I have added oxygens on the right side of my equation, which means that I will have to add oxygens to the left side of my equation. And since water has oxygens, I'm going to write water on my left side, and in order to balance those two oxygens that I have on the right, I would need to have 2 water molecules added here. Overall, I can see that I have 3 hydrogens on the left plus 4 more hydrogens from the waters, so that is 7 hydrogens combined. I'll note that down. On my right side right now, I only have 1 hydrogen over here, so I am missing 6 hydrogens, which means that to balance that out, I am going to add 6 protons over here on the right side to make it all balanced. Now, when we are balanced in terms of the atoms, we need to balance our charge. The overall charge on the left side over here is, well, 0, while the overall charge on the right side over here is going to be +6 from these 6 protons that I have over here on the right. Which means that to balance this equation, I would have to add 6 electrons onto the right side of my equation. So the oxidation portion of my equation is balanced. Now let's go over the reduction portion. So the oxidizing agent that is being reduced in this reaction is permanganate ion. So I'm going to show MnO4, and that ion is negatively charged, so I'm going to indicate that charge. When it comes to these reactions, it is important to know what the reduction or oxidation is going to give you, and in case of the permanganate, we are going to end up with the manganese +2 ion as our product here. So I can see right away here that on the left side of my equation, I have oxygens, and I don't have any oxygens on the right side. So in order to balance that part, I'm going to have 4 water molecules on the right, so I'm going to write +4 H2O molecules over here on the right, which means that I would have to add 8 protons on the left side, like so. Now, in terms of the atoms, we are balanced, and now we need to balance our charge. Combined charge on the left side is going to be +7, while on the right side I have the combined charge of +2, which means that I need to add 5 electrons to the left side to balance it all out. And since electrons are negatively charged, 5 electrons plus 8 protons plus 1 minus from the MnO4 gives me the overall charge of +2. So now both oxidation and reduction portions of my equation are all balanced. But I cannot combine them just yet, because when we are dealing with the redox reactions, we need to make sure that we balance our electrons when we are combining our reactions. I have 5 electrons in my reduction reaction, and I have 6 electrons in my oxidation reaction. Those guys need to be canceling out when I combine my equations, which means that I would have to multiply the top by 5, and I would have to multiply the bottom line by 6. So combining it all together, I will start by taking my reactants on each side and multiplying them by the corresponding numbers and putting them together on the reactant side. So I have 5 toluene molecules plus 10 H2Os plus 6 permanganates plus 48 protons and 30 electrons. Likewise, looking at my product side, I'm going to end up with 5 equivalents of the benzoic acid plus 30 protons plus 6 manganese ions, 24 water molecules, and finally we have 30 electrons on this end as well. Now, canceling the same components on each side, first of all, I'm going to cancel my electrons on the reagent side and on the product side. Then the next thing that I'm seeing is water. On the left side I have 10 waters, so that is going to cancel, and on the right side I have 24 waters, so we are going to end up with only 14 water molecules as a leftover. On top of that, we have protons on both sides, so we have 30 protons on the right side and 48 on the left, so out of those 48, we are only going to end up with 18 protons. So cleaning up my reactant side, I will end up with 5 equivalents of toluene, 6 equivalents of permanganate, 18 protons, giving me 5 equivalents of the benzoic acid, 6 manganese ions, and 14 equivalents of water. And since I know that I am doing this reaction in the presence of the sulfuric acid, I am going to be using the sulfate ion to balance out my ions to make sure that I don't have just, ions floating around and I have the actual physical molecules there. So adding the leftover ions that I have, potassium from permanganate, the sulfate from sulfuric acid and all of that, which gives me my final equation where I have 5 equivalents of toluene reacting with 6 equivalents of potassium permanganate in the presence of 9 equivalents of sulfuric acid, giving us 5 equivalents of benzoic acid, and then our other stuff that we don't really care much about. And I have highlighted all of my spectator ions in orange here, because those guys are irrelevant. But I still need to show them for the complete balanced equation. So now we know that in order to do the benzylic oxidation of toluene to benzoic acid in the presence of potassium permanganate, you need to have 6 equivalents of potassium permanganate for 5 equivalents of the toluene, and we will also require 9 equivalents of sulfuric acid for this reaction to run smoothly. Who would have thought? Here is another fairly straightforward oxidation reaction, the Jones oxidation reaction. From the mechanistic perspective, we show this reaction as something that has 2 rounds of oxidation. First we make an aldehyde, and then from the aldehyde we are going to produce our carboxylic acid. So it might seem like for each 1 equivalent of your alcohol, you would require 2 equivalents of the chromic acid or chromium oxide, like what I have over here in this equation. But let's actually check it by balancing our reaction. Like before, I'm going to start with my oxidation beat. Here I have the alcohol being oxidized to the carboxylic acid, and in order to make sure that I don't lose any atoms, I am actually going to show those 2 implicit hydrogens that we have on our first carbon. So this portion of the molecule, the propyl group, essentially stays unchanged throughout the reaction, so I'm just going to ignore that and pay my attention to what is actually changing. So what I see is that I am adding an extra oxygen to my molecule on the right overall, which means that I would require a water molecule on the left side, so I'm going to bring this H2O. That is going to be the source overall on paper of my oxygen. Then I see that on the left side I have 1, 2, 3, 4, 5 hydrogens, while on the right side I currently am only seeing 1 hydrogen, which means that I also need to add 4 protons onto the right side of my equation, so it balances my atoms. Now, from the perspective of the charge, there is no charge on the left side. On the right, I have a +4 charge overall, so to balance that, I would have to add 4 electrons onto the right side like that. Now it is balanced. Now, when it comes to the reduction part, we are going from chromium oxide to a chromium plus 3 ion. I know that mechanistically we show that some nonsense with chromium and 3 oxygens around it with the oxidation state of plus 4. That thing has nothing to do with the reality. The actual final product in the Jones oxidation when it comes to our chromium is green chromium plus 3. So in order to balance this reaction, I would have to add 6 protons onto the left side, which going to give me 3 waters, 3 H2O molecules on the right to balance my oxygens and my hydrogens. Now, from the charge perspective, I have a plus 6 charge on the left and I have a plus 3 charge on the right, which means that I would have to add 3 electrons to the left side of my equation to balance that out. And like before, I need to make sure that I balance my electrons when combining my equations, meaning that I would have to multiply the top equation by 3 and the bottom equation by 4 when putting it all together. So, from the perspective of my reactants, I would have 3 equivalents of my butanol, 3 equivalents of water, 4 equivalents of chromium oxide, 24 protons, and of course 12 electrons. And on my product side, I'm going to be looking at the 3 equivalents of my butanoic acid, 12 protons, 4 chromium ions, 12 water molecules, and of course 12 electrons that I need to balance out, so I'm going to go ahead and I will cross my electrons right away. Then, when it comes to water, I have 3 extra waters on the left side, which means that on the right I'm going to have 9 waters left. And when it comes to my protons, I have 12 protons over here, which means I only have 12 protons left on the reagent side. So, cleaning up my equation, I'm going to end up with 3 equivalents of my alcohol, my butanol, 4 equivalents of chromium oxide, 12 protons, giving me 3 equivalents of butanoic acid, 4 chromium ions, and 9 equivalents of water. And finally, adding my spectator ions, which in this case is the sulfate ion, I can see that for each 3 equivalents of my alcohol, I would need 4 equivalents of chromium oxide or chromic acid in order to accomplish the Jones oxidation. So in reality, it's not a 1:2 ratio as mechanism might have suggested. And without balancing your reaction, you could have potentially overused or underused one of your reagents, leading potentially to an unwanted effects or unwanted products or co-products. And while we don't usually ask students to balance the redox reactions on the exams, don't be surprised if your instructor decides to throw that at you as a curved ball or, extra bonus question type of a deal. And talking of extra points, how about this reaction over here? This is also Jones oxidation, but instead of the carboxylic acid, we are going to end up with a ketone. So my challenge to you is balance this reaction and tell me in the comments what is going to be the ratio of alcohol to the chromic acid that you are going to see in the balanced reaction. And as always, thank you for watching. If you learned something new today, boop that like button and subscribe for more. Check out this video next, and I will see you next time.